You are impossible. Every atom in your body, every breath you take, every thought firing through your neurons exists because the universe breaks its own rules. Right now, electrons in your cells are doing something that classical physics says cannot happen. They are passing through walls. Not metaphorically, literally tunneling through barriers that should be impenetrable. This is not science fiction. This is quantum tunneling, and it is the most important phenomenon you have never heard of. Without it, stars would never ignite. Nuclear fusion would be impossible. The sun would be a cold, dead rock. DNA would fall apart. Computer chips would not work, and you would simply not exist. Scientists have discovered that quantum tunneling does not just make life possible. It might let us see through walls, teleport information instantly, and even achieve nuclear fusion in our basements. The technology emerging from this bizarre quirk of reality is about to change everything. If you are ready to discover how the universe cheats physics, hit that subscribe button because we are diving into the strangest confirmed fact about reality. Let's begin. Isaac Newton gave us a universe that made perfect sense. Objects at rest stay at rest. Apply force and things move predictably. Throw a ball at a wall and it bounces back. Every action has an equal and opposite reaction. The cosmos operated like clockwork, deterministic and comprehensible. For 200 years, this mechanical units following predictable paths. Instead, they existed in fuzzy probability clouds, somehow occupying multiple positions simultaneously until measured. Light behaved as both a wave and a particle depending on how you observed it. Particles appeared and disappeared randomly. Cause and effect became blurry. The deterministic clockwork universe crumbled when examined at microscopic scales. Max Planck discovered that energy comes in discrete packets called quanta, not smooth continuous flows. Einstein found that light consists of particles called photons, even though experiments clearly showed it travels as waves. Niels Bohr revealed that electrons jump between energy levels without traversing the space in between, vanishing from one location and appearing in another instantaneously. The weirdness accelerates protons and entire atoms behave as waves under the right conditions. Particles have wavelengths. Waves have momentum. The distinction between matter and energy blurred into quantum superposition. Experiments confirmed these bizarre predictions with disturbing accuracy. The double-slit experiment showed single electrons interfering with themselves, passing through two openings simultaneously like waves, then hitting a detector screen as localized particles. Matter was wave-like and particle-like at the same time, with the distinction depending on whether anyone was watching. The scientific community resisted these conclusions. Einstein himself spent decades trying to prove quantum mechanics was incomplete, insisting that God does not play dice with the universe. But every challenge only strengthened the theory. Every experiment designed to expose its flaws instead confirmed its predictions. Quantum mechanics was not just correct, it was frighteningly accurate, predicting experimental results to 10 decimal places. By the 1930s, physicists had developed a complete mathematical framework describing the quantum world. The equations worked perfectly. The predictions matched reality precisely. The problem was nobody understood what the math actually meant. How could particles exist in multiple states simultaneously? How could observation change reality? What was waving when a wave function propagated? The calculations were clear, but the implications were insane. Yet buried in this mathematical strangeness was something even more disturbing. The equations predicted that particles could do something that violated the most basic intuition about how objects move. They could pass through solid barriers without breaking them. They could appear on the other side of walls without ever crossing the space in between. They could tunnel. Classical physics says you need enough energy to climb over a barrier. Roll a ball toward a hill and it will only reach the top if it is moving fast enough. If the ball lacks sufficient energy, it rolls back down. It never appears on the other side without going over the top. This is obvious. This is how reality works. Except at quantum scales, it does not work that way at all. Particles can and do pass through barriers. They do not have enough energy to cross. George Gamow first recognized this in 1928 while studying radioactive decay. Alpha particles trapped inside atomic nuclei were escaping despite lacking the energy to overcome the nuclear force holding them in. Classical physics said this was impossible. The particles were like prisoners locked in cells with walls they could not possibly climb. Yet somehow they were getting out. Gamow applied the newly developed quantum mechanics and discovered the answer. Particles are described by wave functions that represent probability distributions. These waves do not stop abruptly at barriers. Instead, they decay exponentially inside the barrier material. On the far side of the barrier, a small portion of the wave function still exists. This means there is a non-zero probability the particle will be found on the other side even though it never had enough energy to cross. The particle tunnels through. Think of it like this. A classical particle facing a barrier is like a person trying to walk through a brick wall. Impossible. But a quantum particle is like a ghost that exists as a probability cloud. Most of the ghost stays on one side, but a faint part extends through the wall. Sometimes when you measure where the ghost is, you find it on the far side. It did not break the wall or climb over it. It simply appeared there because quantum mechanics allows this. The mathematics describing tunneling is precise. The probability of tunneling depends on the barrier height, the barrier width, and the particle's energy. Tall, thick barriers are hard to tunnel through. Low, thin barriers are easier. Lighter particles tunnel more readily than heavy ones because quantum effects are more pronounced for low-mass particles. Electrons tunnel easily. Protons tunnel less so. Entire atoms almost never tunnel because they are too heavy. The probability drops exponentially with increasing barrier width. Make a barrier twice as thick and the tunneling probability does not just halve. It drops by orders of magnitude. This is why we do not see baseballs tunneling through walls. For macroscopic objects, the probability becomes so infinitesimally small that it effectively never happens. But for subatomic particles facing nanometer-scale barriers, tunneling is routine. Experiments demonstrated this conclusively. Scientists could measure electrons appearing on the far side of barriers without passing through them. The phenomenon was real, measurable, and completely inconsistent with any classical understanding of motion. Objects were not traveling from point A to point B by moving through the intervening space. They were probability distributions that collapsed into definite locations according to quantum rules that permitted them to be found in places they should not reach. The implications were staggering. If particles could tunnel through barriers, then nothing was truly impenetrable at quantum scales. Electrons could escape from atoms. Protons could fuse inside stellar cores despite electrostatic repulsion. Chemical reactions that seemed impossible based on energy requirements could occur anyway through quantum mechanical pathways. The universe had a built-in cheat code that allowed particles to occasionally violate classical physics and do impossible things. And this cheat code was not rare or exotic. It was fundamental. Tunneling happened constantly, everywhere, in every atom and molecule. It was as basic to reality as gravity or electromagnetism. The universe ran on quantum tunneling. We just had not noticed because our everyday experience involves objects too large for quantum effects to matter. But once scientists understood tunneling, they started seeing it everywhere. And they realized it explains something that had puzzled astronomers for decades: how stars actually work. The sun has been burning for 4.5 billion years, pouring out energy at a rate of 400 trillion watts every single second. Where does this energy come from? For centuries, nobody knew. Coal and chemical reactions could not possibly fuel it for that long. Gravitational contraction provided some energy, but not nearly enough. The sun's power source remained a complete mystery. Then scientists discovered nuclear fusion. Smash hydrogen nuclei together with enough force and they combine into helium, releasing enormous energy in the process. Einstein's equation equals mc² showed that tiny amounts of mass convert into huge amounts of energy. The sun could be a giant fusion reactor converting hydrogen into helium and mass into light. The problem was the math did not work. Hydrogen nuclei are protons, positively charged particles that repel each other through electromagnetic force. To fuse, two protons must get close enough for the strong nuclear force to bind them together. But the electromagnetic repulsion is immense. Classical calculations showed that protons in the sun's core, despite temperatures of 15 million degrees, simply do not have enough kinetic energy to overcome this repulsion and touch. The sun should not be able to sustain fusion. It should be cold and dark, but it is not. In the 1920s, physicists realized quantum tunneling solved the mystery. Protons do not need to overcome the electromagnetic barrier classically. Their wave functions extend through the barrier. Sometimes when two protons approach each other, they quantum tunnel through the electromagnetic repulsion and suddenly find themselves close enough for the strong force to grab them. Fusion occurs not because the protons have sufficient energy, but because quantum mechanics allows them to occasionally cheat past the energy requirement. The calculations transformed. With tunneling included, fusion rates in the sun's core matched observations perfectly. The sun works because quantum tunneling allows nuclear fusion to occur at temperatures and pressures that would be completely insufficient classically. Every photon of sunlight reaching Earth exists because protons deep in the solar core tunneled through electromagnetic barriers billions of times per second. Without tunneling, the sun never would have ignited. Our solar system would be a frozen waste orbiting a ball of inert hydrogen. Earth would be a lifeless ice rock drifting through darkness. Life would never have emerged because the energy source powering it would not exist. Quantum tunneling does not just explain how stars work. It explains why they can exist at all. Every star in the night sky is a fusion reactor operating on quantum mechanical principles. The universe is full of celestial bodies that burn because subatomic particles can do impossible things. Scientists calculated exactly how much tunneling increases fusion rates. For the proton-proton fusion that powers the sun, tunneling enhances the reaction rate by a factor of 10 to the power of 30. Without tunneling, the reaction rate would be 10 million trillion times slower. The sun would produce essentially no energy at all. This is not a small correction to classical physics. This is the difference between a universe full of burning stars and a universe of cold darkness. The same principle applies to all stars regardless of size. Massive stars burn faster because their higher core temperatures and pressures increase tunneling probabilities. Small red dwarfs burn slowly because lower temperatures mean less tunneling. But all of them depend fundamentally on quantum mechanics permitting fusion reactions that classical physics forbids. Hydrogen bombs work the same way. The fusion weapons developed in the 1950s rely on quantum tunneling to merge hydrogen isotopes into helium. Scientists had to engineer conditions where tunneling probabilities became high enough for explosive fusion. Without understanding quantum tunneling, nuclear fusion weapons could not have been designed. Fusion reactors being developed today face the same challenge. We are trying to create conditions where hydrogen isotopes tunnel together frequently enough to generate net energy output. Achieving sustained fusion requires precisely controlling temperatures, pressures, and confinement times to maximize tunneling rates. Multiple research projects around the world are inching closer to practical fusion power generation. The ITER reactor under construction in France aims to demonstrate sustained fusion by heating hydrogen isotopes to 150 million degrees Celsius, 10 times hotter than the sun's core. At these temperatures, tunneling probabilities increase enough to achieve fusion even with lower pressures than exist in stellar cores. If successful, fusion reactors could provide virtually unlimited clean energy. No carbon emissions, no radioactive waste with million-year half-lives. Just helium and energy extracted from water converted to power through quantum tunneling. The same effect that makes stars burn could solve humanity's energy crisis. Every major fusion research facility depends on quantum tunneling calculations to design plasma confinement systems and predict reaction rates. Engineers optimize magnetic bottle shapes and heating systems to maximize the probability that deuterium and tritium nuclei tunnel together. The entire enterprise of fusion energy rests on a quantum mechanical phenomenon that classical physics says should not happen. But stars and fusion reactors are just the beginning. Tunneling enables something even more fundamental to existence. It holds DNA together and tears it apart. Every cell in your body contains DNA, the twisted double helix molecule that stores genetic information in sequences of chemical bases. 4 bases pair up in specific combinations. Adenine bonds with thymine. Guanine bonds with cytosine. These bonds form through hydrogen bridges, relatively weak electromagnetic attractions that hold the 2 strands together. The structure is elegant and stable. The problem is the bonds should not be that stable. Classical chemistry predicts that thermal fluctuations at body temperature should constantly break these hydrogen bonds, causing DNA strands to unzip spontaneously. Your genetic code should be falling apart constantly, scrambled by random molecular vibrations. But it does not. DNA remains stable for years. Cells copy it reliably. Mutations are rare rather than constant. Why? Quantum tunneling provides the answer. Hydrogen atoms in the bonds between DNA bases can quantum tunnel between different positions. This tunneling stabilizes the bonds by allowing protons to find energetically favorable configurations that classical particles could not reach. The bonds become stronger because quantum mechanics permits arrangements that optimize electromagnetic attraction. Scientists discovered this in the 1960s when detailed studies of DNA structure revealed that hydrogen bond stability exceeded classical predictions. The only explanation was quantum mechanical behavior of protons in the bonds. Perlov-Lodin proposed that proton tunneling could also cause mutations. If a proton tunnels from one base to another during DNA replication, it creates a mismatch. Adenine might temporarily pair with cytosine instead of thymine. When the cell copies this mismatched section, it introduces an error in the genetic sequence. A mutation occurs not through chemical damage but through quantum mechanical proton transfer. This means evolution itself may be partially driven by quantum tunneling. Random mutations provide the variation that natural selection acts upon. If some of those mutations result from protons tunneling between DNA bases, then quantum mechanics directly influences biological evolution. The changes that create new species and drive adaptation arise partly from subatomic particles doing impossible things. The implications are profound. Life is not just chemistry. It is quantum chemistry. Biological processes depend on quantum mechanical effects that have no classical explanation. Enzymes catalyze reactions by lowering energy barriers, but the actual chemistry often involves quantum tunneling of protons or electrons through those reduced barriers. Your cells are quantum machines. Photosynthesis relies on quantum tunneling too. Plants capture sunlight and convert it to chemical energy with near-perfect efficiency. Classical models cannot explain this. The electrons excited by absorbed photons must transfer between molecules faster than classical physics allows. Quantum tunneling enables these electron transfers, allowing energy to flow through photosynthetic complexes without being lost as heat. Recent research suggests quantum effects in photosynthesis are even more exotic than tunneling alone. Electrons may exist in quantum superposition, exploring multiple pathways simultaneously and selecting the most efficient route. Birds navigate using Earth's magnetic field through quantum processes in their eyes. Enzymes in your body function through quantum tunneling of hydrogen atoms. Even your sense of smell may involve quantum mechanics, with molecules recognized not just by shape but by quantum vibrations. The boundary between classical biology and quantum physics is dissolving. Life operates at the interface where quantum effects become large enough to matter, but not so large that they dominate. Evolution has apparently learned to exploit quantum mechanical phenomena for biological advantage. But tunneling does not just stabilize DNA and enable mutations. It also regulates the chemical reactions that destroy and rebuild molecules in your cells. Enzymes speed up reactions by allowing quantum tunneling through energy barriers. Without this, metabolism would be impossibly slow. The carefully controlled chemistry keeping you alive depends on quantum particles cheating past classical barriers thousands of times per second in every cell. Oxygen you breathe, food you digest, energy your muscles generate all involve quantum tunneling at some step. You are not just made of quantum particles. You are a quantum process, a temporary arrangement of atoms held together and transformed by effects that defy classical explanation. The carbon in your cells, the calcium in your bones, the iron in your blood all originated in stars where quantum tunneling enabled fusion. Then quantum tunneling enabled those atoms to form molecules, catalyzed the reactions that build complex organic compounds, stabilized the DNA that encodes you, and continues regulating the chemistry that sustains your consciousness moment to moment. You exist because the universe breaks its own rules. But that is still not the strangest application of quantum tunneling. Scientists have built machines that exploit it in ways that might seem like magic. In 1981, two scientists at IBM named Gerd Binnig and Heinrich Rohrer invented a device that seemed impossible. They called it a scanning tunneling microscope, and it could image individual atoms, not molecules or clusters. Single atoms sitting on surfaces, resolved with such clarity you could count them and measure distances between them. The resolution was so fine it made electron microscopes look blind. How did they achieve this? Quantum tunneling. The scanning tunneling microscope works by bringing an incredibly sharp metal tip, sharpened down to a single atom at its point, extremely close to a surface. The tip never touches the surface. A gap of just a few nanometers separates them. Classical physics says no current should flow across this gap because air is an insulator. But electrons are quantum particles. Their wave functions extend through the gap. When voltage is applied between the tip and the surface, electrons quantum tunnel across the empty space. The tunneling current is extraordinarily sensitive to distance. Move the tip 1 nanometer closer and the current increases by a factor of 1,000. This sensitivity allows the microscope to measure height variations at the atomic scale. As the tip scans across a surface, a feedback system adjusts the tip's height to keep the tunneling current constant. The height adjustments create a map of the surface topography with atomic resolution. Scientists can literally see the bumps where individual atoms sit. The images produced are stunning. You can see the hexagonal lattice of carbon atoms in graphite. You can observe the arrangement of silicon atoms on a semiconductor surface. You can watch molecules attach and detach from surfaces in real time. The scanning tunneling microscope opened a window into the atomic world that had been completely invisible before. Binnig and Rohrer won the Nobel Prize in 1986, just 5 years after inventing the device. The impact on science was immediate and revolutionary. Materials scientists could study how atoms arrange themselves on surfaces, leading to better understanding of catalysts, semiconductors, and nanotechnology. Chemists could observe chemical reactions at the molecular level. Physicists could probe quantum phenomena directly. The entire field of nanoscience exploded because researchers could finally see what they were working with. But the scanning tunneling microscope does more than just image atoms. It can manipulate them. By increasing the voltage and bringing the tip very close to a specific atom, scientists can use tunneling electrons to push atoms around on surfaces like microscopic bulldozers. In 1989, IBM researchers famously arranged 35 xenon atoms on a copper surface to spell out the company name. Each letter was several nanometers tall, written in individual atoms. This was not an accident or a natural formation. It was deliberate atom-by-atom construction using quantum tunneling to manipulate matter at the smallest possible scale. The technique opened possibilities that seemed like science fiction. Scientists began building molecular machines, tiny gears and switches made of individual molecules positioned precisely using scanning tunneling microscopes. They created quantum corrals, circular arrangements of atoms that trap electron waves, allowing direct observation of quantum wave functions. They tested quantum computing concepts by building logic gates from single atoms. The ability to manipulate individual atoms transformed abstract quantum mechanics into hands-on engineering. Researchers could design structures atom by atom, test quantum phenomena directly, and build devices at scales where classical physics completely breaks down. Every smartphone, every computer chip, every modern electronic device depends on manufacturing processes that descended from knowledge gained through scanning tunneling microscopy. Semiconductor engineers need to control how atoms distribute themselves in silicon to create transistors. Understanding surface structures at atomic resolution enabled the miniaturization that led to billion transistor processors. Modern electronics exists because quantum tunneling let us see and manipulate atoms. But scanning tunneling microscopes revealed something even more important. They proved quantum mechanics was not just abstract math. It was tangible reality that could be measured, observed, and exploited. Seeing individual atoms arranged on surfaces, watching their electrons tunnel between energy states, manipulating quantum systems with atomic precision eliminated any remaining doubt about whether quantum weirdness was real. It was real, and it was useful. Today, thousands of scanning tunneling microscopes operate in research labs and industrial facilities worldwide. Modified versions probe magnetic properties, chemical structures, and electronic states. The basic principle remains the same. Use quantum tunneling to sense the atomic world with impossible precision. The device that launched nanotechnology and revolutionized materials science works entirely because electrons can pass through gaps they should not be able to cross. Without tunneling, scanning tunneling microscopes could not exist. We would still be blind to the atomic world, guessing at structures we could never observe. Binnig and Rohrer's genius was recognizing that a quantum mechanical impossibility could become a practical measurement tool. But electron tunneling enables something even more important to modern life. It makes your computer possible. Every transistor in the processor running your phone or computer operates using quantum tunneling. Modern chips contain billions of transistors, each just nanometers across. At these scales, classical physics breaks down completely. The devices only function because designers account for quantum effects. The basic transistor is a switch controlled by voltage. Apply voltage to the gate and current flows between source and drain. Remove voltage and current stops. Digital logic depends on these binary states. But shrinking transistors to nanometer scales creates problems. The insulating layer separating the gate from the channel beneath it becomes so thin that electrons start tunneling through it even when the transistor should be off. This is called gate leakage. Classical insulators stop working when they are just a few atomic layers thick because electrons tunnel through them easily. Engineers solved this by designing transistors that exploit tunneling deliberately rather than fighting it. Modern processors use high-K metal gate transistors with carefully engineered insulator materials that permit controlled tunneling. The devices work with tunneling rather than against it. Flash memory, the technology storing data in USB drives and solid-state drives, relies entirely on quantum tunneling. Each memory cell traps electrons in a floating gate surrounded by insulators. Writing data involves applying voltage that forces electrons to tunnel through the insulator into the gate. Reading data detects whether electrons are trapped in the gate. Erasing data applies opposite voltage that makes electrons tunnel back out. Your files, photos, and programs exist as patterns of trapped electrons stored by forcing them to quantum tunnel through barriers. The erase-write cycles that flash memory can endure before wearing out are limited by how many times electrons can tunnel through insulators before damaging them. Everything digital is temporary because quantum tunneling gradually degrades the barriers that trap data. Moore's law, the observation that transistor counts double every 2 years, continued as long as it did, partly because engineers learned to work with quantum tunneling. Each new generation of chips shrank transistors further into the quantum regime where tunneling effects dominate. Designing processors became an exercise in quantum engineering. Today's most advanced chips use transistors with features just 3 nanometers across. At this scale, quantum effects are not minor corrections. They are primary design considerations. Electrons tunnel readily across such tiny structures. Quantum interference affects how current flows. Wave functions of adjacent transistors overlap. Engineers must solve quantum mechanical equations to predict device behavior. Without understanding tunneling, modern computing would not exist. We would have hit a miniaturization wall decades ago when transistors became so small that electrons started leaking through their insulators. The entire digital revolution happened because physicists and engineers learned to design around and eventually exploit quantum mechanical effects. The smartphone in your pocket contains more computing power than existed in the entire world in 1950. This happened because devices shrank from room-sized machines to handheld tablets. That shrinkage was only possible because we understood quantum tunneling well enough to design transistors that function in regimes where classical physics completely fails. Every message you send, every photo you take, every video you stream depends on billions of transistors exploiting quantum mechanical effects that should not exist according to classical physics. The digital world is fundamentally quantum, but tunneling in electronics creates problems too. As transistors shrink further, unwanted tunneling becomes harder to control. Electrons tunnel between components that should be isolated. Power consumption increases as leakage currents flow where they should not. Heat generation becomes a major challenge. Some researchers argue we are approaching fundamental limits where tunneling effects will prevent further miniaturization. Transistors cannot shrink forever because eventually they become so small that quantum tunneling destroys their function. Electrons tunnel freely through barriers too thin to block them. The devices stop acting like switches and become uncontrollable. This might end Moore's law within the next decade unless completely new transistor designs emerge. Others see opportunity in these challenges. What if we design computers that use tunneling as the primary operating principle instead of treating it as a problem to minimize? Quantum computers take this approach. They exploit quantum superposition and entanglement to perform calculations impossible for classical machines. Tunneling plays a crucial role in quantum computing too. Quantum bits must tunnel between energy states to perform operations. Superconducting qubits, one of the leading quantum computer architectures, use Josephson junctions where The future of computing will be even more quantum than the present. As devices shrink further into the realm where tunneling dominates, we must design with quantum mechanics as the foundation rather than an inconvenient complication. The impossible will become routine. And beyond computing, tunneling enables technologies even stranger. Quantum tunneling does not just allow electrons to pass through barriers. It allows entire atoms to do so under the right conditions. This has led to one of the strangest and most potentially revolutionary technologies. Scanning tunneling microscopy inspired scientists to think about tunneling in new ways. If you can measure tunneling currents with atomic precision, what else might be possible? Researchers began exploring whether tunneling could enable new types of sensors, energy devices, and systems small and cheap enough for everyday use. Early research suggests this could diagnose neurological conditions that current technology cannot detect. Chemical sensing represents another frontier. Tunneling electrons are extraordinarily sensitive to molecular structures. Devices using tunneling currents can identify specific molecules by their unique electronic signatures. This could lead to handheld sensors that detect explosives, chemical weapons, pollutants, or disease markers in breath or blood samples. Several companies are developing tunneling-based sensors for medical diagnostics. The idea is to detect disease-related molecules at concentrations far below what conventional sensors can measure. A single cancer cell releases molecular markers. Quantum tunneling sensors might catch these markers years before the disease becomes detectable through traditional means. Energy harvesting applications are emerging too. Some researchers explore whether quantum tunneling could enable new types of solar cells that convert light to electricity more efficiently than current photovoltaic technology. By designing nanostructures where electrons tunnel between carefully arranged energy levels, it might be possible to capture more of the solar spectrum and reduce waste heat. Thermoelectric devices that convert waste heat to electricity also benefit from tunneling. Materials engineered to enhance tunneling can transport charge carriers more efficiently, improving power generation from temperature differences. This could make better generators for spacecraft, industrial plants, or even wearable electronics powered by body heat. Nuclear batteries using radioactive decay might seem dangerous, but they provide steady power for decades. Spacecraft use them when solar panels are impractical. These batteries work because alpha particles tunnel out of radioactive nuclei, creating ionization that generates current. Understanding tunneling better could lead to safer, more efficient designs. Some theoretical proposals suggest quantum tunneling might enable room temperature superconductors. Normal superconductors only work at extreme cold because thermal vibrations destroy the quantum states needed for resistance-free current flow. But if materials could be engineered where electrons tunnel through barriers that block thermal disruption, superconductivity might persist at higher temperatures. This remains highly speculative, but the potential impact would be revolutionary. The most exotic application might be quantum communication systems. While information cannot travel faster than light, quantum entanglement allows correlated measurements across vast distances. Tunneling plays a role in creating and detecting entangled states. Networks of quantum sensors connected through entanglement could enable communication systems that are fundamentally impossible to intercept or jam. China has already launched quantum communication satellites using these principles. The encryption keys are secured by quantum mechanics itself. Any attempt to intercept the communication destroys the quantum states, immediately alerting both parties. This is not better encryption. It is mathematically unbreakable security guaranteed by the laws of physics. Extending this technology requires better sources of entangled particles and more sensitive detectors. Both areas benefit from understanding quantum tunneling. Engineers optimize tunneling rates in photon detectors and tune tunneling barriers in quantum dot systems that generate entangled photons. The quantum internet being developed by researchers worldwide will rely on tunneling-based technologies at multiple levels. But perhaps the most immediate application of tunneling research is achieving the energy breakthrough humanity desperately needs: controlled fusion power. Fusion energy promises nearly unlimited clean power. Fuel is abundant. Deuterium can be extracted from seawater. Tritium can be bred from lithium. The products are helium and neutrons. No carbon emissions. No long-lived radioactive waste. Energy density millions of times higher than chemical fuels. It sounds too good to be true. The challenge is creating conditions where hydrogen isotopes tunnel together frequently enough to sustain reactions that produce more energy than they consume. This requires temperatures exceeding 100 million degrees Celsius and confinement times long enough for sufficient fusion to occur. Scientists have pursued this goal for 70 years. Progress has been frustratingly slow. Every advance revealed new complications: plasma instabilities, energy losses, material challenges. Each problem required years to solve. But recently, momentum has accelerated. The National Ignition Facility achieved fusion ignition in 2022, producing more energy from fusion than the lasers delivered to the fuel capsule. This was a historic milestone. It proved that energy gain from fusion is achievable, not just theoretically possible but actually demonstrated. The technique used inertial confinement. Powerful lasers compress a tiny fuel pellet to extreme density and temperature for a few nanoseconds. Under these conditions, deuterium and tritium nuclei tunnel together rapidly enough that fusion cascades through the fuel before it explodes apart. The challenge is scaling this to practical power generation. Magnetic confinement takes a different approach. Powerful magnetic fields trap hot plasma in a toroidal chamber, holding it away from the walls while fusion occurs. The ITER project under construction in France is the largest magnetic confinement experiment ever attempted. It aims to demonstrate sustained fusion with significant energy gain. ITER will heat deuterium-tritium plasma to 150 million degrees Celsius, about 10 times hotter than the sun's core. At these temperatures, the kinetic energy of nuclei increases substantially, but they still tunnel through electromagnetic barriers to fuse. The reaction rate depends critically on the tunneling probability, which physicists calculate using quantum mechanics. Private companies are pursuing fusion too. Commonwealth Fusion Systems, backed by substantial venture capital, is building a smaller reactor using high-temperature superconducting magnets. TE Technologies explores alternative fusion reactions. Helion Energy is developing a different magnetic confinement approach. Over 30 companies worldwide are racing to achieve commercial fusion power. All of them depend fundamentally on quantum tunneling. Their reactor designs optimize conditions to maximize tunneling rates. Engineers calculate plasma temperatures, densities, and confinement times needed to make tunneling frequent enough for net energy production. The entire field exists because quantum mechanics allows nuclei to fuse at temperatures and pressures far below what classical physics would require. If fusion succeeds as an energy source, it will represent the ultimate practical application of quantum tunneling. The same phenomenon that makes stars burn will power human civilization. Energy too cheap to meter becomes possible. Climate change could be mitigated. Water scarcity solved through desalination. Industrial processes requiring intense heat become economical. The implications extend beyond Earth. Fusion-powered spacecraft could reach Mars in weeks rather than months. They could explore the outer solar system with capabilities far exceeding anything chemical rockets enable. Interstellar probes might achieve significant fractions of light speed through sustained fusion thrust. Humanity's energy future might be secured by subatomic particles doing impossible things. Protons tunneling together in reactors on Earth just as they tunnel together in the cores of stars. The universe's cheat code could save civilization. But there is something even stranger about tunneling. Recent discoveries suggest it might not be random after all. Quantum tunneling probabilities are calculated precisely. Given a barrier height, width, and particle energy, physics equations predict exactly how often tunneling will occur. These predictions match experiments with remarkable accuracy. But they describe probabilities, not certainties. You can calculate that one particle in a million will tunnel through a barrier, but you cannot predict which specific particle will succeed. Or can you? Recent experiments hint that tunneling might be more deterministic than previously thought. In 2019, researchers used ultrafast lasers to track electron tunneling in real time. They measured how long tunneling takes, something physicists debated for decades. The answer surprised everyone. Tunneling appears to be instantaneous. More precisely, it happens faster than any known physical process can measure. Electrons on one side of a barrier appear on the other side without any detectable transit time through the barrier. This is not just fast, it is zero duration. The electron does not travel through the barrier. It stops existing in one location and starts existing in another without traversing the space between. The implications are unsettling. If tunneling is truly instantaneous, then particles are somehow relocating without moving. This seems to violate causality until you remember that quantum particles are not little balls traveling along paths. They are wave functions, probability distributions that exist in multiple locations simultaneously until measured. The wave function extends on both sides of the barrier. Measurement collapses the wave function to a definite location, which might be on either side. From this perspective, tunneling is not the particle crossing the barrier. It is the wave function collapsing to the far side rather than the near side. This raises profound questions. If tunneling is instantaneous, can information travel faster than light through tunneling? The answer appears to be no. While the particle relocates instantly, you cannot control which particle tunnels or when. The randomness prevents using tunneling to send information faster than light. Causality remains protected. But some physicists wonder if deeper layers exist beneath the probabilities. What if quantum randomness is not fundamental but reflects hidden variables we have not discovered yet? What if particles follow deterministic rules that we simply cannot observe? This idea dates back to Einstein, who insisted quantum mechanics must be incomplete. Hidden variable theories propose that particles have definite properties at all times, but those properties are hidden from us by the measurement process itself. If true, then tunneling might be perfectly predictable if we knew the hidden variables. Experiments testing hidden variable theories have mostly ruled them out. Bell's theorem and countless experiments show that quantum correlations cannot be explained by local hidden variables. The universe really is probabilistic at its core, not deterministic. Yet loopholes remain. Non-local hidden variables or retrocausal influences might still be possible. Some interpretations of quantum mechanics suggest the future influences the past through quantum processes. Particles might somehow know where they will be measured and adjust their behavior accordingly. This sounds absurd until you remember that quantum mechanics already requires accepting absurdities. Particles existing in multiple states simultaneously. Observation changing reality. Entangled particles correlating instantaneously across cosmic distances. The universe already violates common sense at every turn. The practical question is whether understanding tunneling better allows greater control. Can we enhance or suppress tunneling rates beyond what standard quantum mechanics predicts? Some research suggests electromagnetic fields can modify tunneling probabilities. Intense laser fields can suppress tunneling that would normally occur or enhance tunneling through barriers that would normally block particles. This field-controlled tunneling could enable new technologies. Imagine transistors that switch faster by using laser pulses to modulate tunneling rates, or chemical reactions activated by light that induces tunneling through energy barriers. The boundary between chemistry and quantum engineering is dissolving. What seems like fundamental randomness might become controllable through techniques we have not discovered yet. The universe has surprised us before. Every time physicists thought they understood reality completely, new experiments revealed deeper layers of strangeness. Quantum mechanics itself was a complete surprise to the classical physicists who first encountered it. Perhaps tunneling hides secrets we will only discover once technology improves enough to probe reality at even finer scales. But whether tunneling is controllable or fundamentally random, one thing is certain. It shaped the universe and made your existence possible. The cosmic microwave background, the faint glow left over from the Big Bang, shows tiny temperature fluctuations. These fluctuations represent quantum variations in the early universe that got amplified by cosmic inflation. Without quantum tunneling and related quantum effects, the universe would have been perfectly uniform. No fluctuations means no galaxies, no stars, no planets, no life. Quantum mechanics made the universe interesting. In the first fractions of a second after the Big Bang, the universe existed in an extremely high energy state called a false vacuum. This state was unstable. It needed to decay to a lower energy true vacuum. The decay happened through quantum tunneling. The entire universe tunneled from the false vacuum to the true vacuum, releasing enormous energy that drove cosmic inflation. Space itself expanded faster than light, growing from subatomic size to astronomical scale in tiny fractions of a second. This inflationary period smoothed out the early universe while amplifying quantum fluctuations into the seeds of cosmic structure. Every galaxy formed around quantum variations that arose through tunneling and related processes during inflation. The observable universe exists in its current form because quantum tunneling triggered inflation. Without this, the cosmos would look completely different, possibly too uniform to generate stars and galaxies at all. Quantum tunneling shaped reality at the largest possible scales. Later, as the universe cooled and particles formed, tunneling continued playing crucial roles. The first atomic nuclei formed through fusion processes enabled by tunneling. The first stars ignited because tunneling allowed fusion in their cores. Those stars created heavy elements through fusion chains dependent on tunneling, then scattered those elements through space when they exploded. The carbon in your body formed in a star that burned through quantum tunneling. The oxygen you breathe, the calcium in your bones, the iron in your blood, all were forged in stellar cores where nuclei tunneled past electromagnetic barriers to fuse. You are made of star matter created by quantum processes. Every atom composing your body participated in tunneling events at some point in its history. When those atoms gathered on early Earth and began forming complex molecules, tunneling helped stabilize chemical bonds. Organic compounds assembled into systems complex enough to reproduce. Life emerged, possibly aided by quantum effects including tunneling that enabled chemical reactions despite energy barriers. Over billions of years, evolution shaped organisms that exploit quantum mechanics for biological advantage. The cells composing you use tunneling in photosynthesis, respiration, and countless enzymatic reactions. Your DNA is stabilized by tunneling. Your thoughts involve quantum processes in neurons. You are not just made of quantum particles. You are a quantum biological system shaped by billions of years of evolution in a universe where tunneling is fundamental. Every sensation you feel, every thought you think, every movement you make involves quantum processes somewhere in the chain of causation. The universe created you through quantum tunneling and sustains you through the same phenomenon. This is not metaphor or poetry. This is literal physical fact confirmed by decades of experimental evidence and theoretical understanding. You exist because impossible things happen constantly, because the universe has a cheat code written into its deepest laws, because particles can do things that should not be possible, because reality at its foundation is stranger than any fiction. And we are only beginning to understand what this means. Quantum tunneling is not finished surprising us. Current research explores whether tunneling plays roles in biological processes beyond what we have already discovered. Some scientists investigate whether quantum effects in the brain might be relevant to consciousness itself. This remains highly controversial. Most neuroscientists argue that brains are too warm and wet for delicate quantum states to survive. Thermal noise should destroy quantum coherence instantly, but some evidence suggests otherwise. Microtubules, protein structures inside neurons, might maintain quantum states for brief periods. If true, this could mean that information processing in brains involves quantum computation in addition to classical neural firing. Consciousness might be partially quantum mechanical. Physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed this decades ago. The idea was widely dismissed as too speculative, but recent experiments show quantum effects in biological systems are more robust than previously thought. Birds navigate using quantum effects in proteins in their eyes. Plants use quantum coherence in photosynthesis. Evolution has apparently learned to exploit and protect quantum states even in warm environments. If brains use quantum processes, tunneling would certainly be involved. Ions passing through membrane channels might tunnel rather than following classical trajectories. Electrons in enzymes might tunnel between molecules to enable reactions. Neurotransmitters might be released through processes involving tunneling. This research is in early stages. Most claims remain unproven, but the possibility that consciousness involves quantum mechanics is no longer dismissed as absurd. The question is being seriously investigated by researchers with proper experimental tools. If quantum tunneling contributes to consciousness, then you are reading these words partly because electrons are passing through barriers they should not be able to cross. Your thoughts exist because the universe permits impossible things. Some philosophers argue that quantum mechanics might explain free will. If neural processes involve quantum tunneling, and tunneling is fundamentally random, then determinism breaks down at the neurological level. Your decisions might not be predetermined by prior causes if quantum randomness plays a role. This does not prove free will exists. Randomness is not the same as choice, but it does show that strict determinism fails in a quantum universe. The future is not inevitable. Multiple possibilities exist simultaneously until observation collapses them into definite outcomes. Whether this grants agency or just replaces determinism with chance remains debated. But the physics is clear. Quantum mechanics, including tunneling, makes the universe genuinely unpredictable in principle, not just in practice. Beyond consciousness, researchers explore exotic applications that sound like science fiction. Could quantum tunneling enable new propulsion systems? Some speculative papers discuss whether engineered vacuum fluctuations might generate thrust. This remains far beyond current technology and may be impossible. But the fact that serious physicists publish papers exploring this shows how quantum mechanics continues opening unexpected possibilities. Could tunneling enable faster than light communication after all? Almost certainly not. Every attempt to send information faster than light through quantum phenomena has failed. The universe appears to have protections preventing causality violations. But researchers keep looking for loopholes because the implications would be revolutionary. Could we tunnel through spacetime itself? Some theories of quantum gravity suggest spacetime is not fundamental but emerges from more basic quantum entities. If true, then spacetime might have a structure that permits tunneling at certain scales or energies. This is wildly speculative, but the math allows it. Understanding spacetime at the quantum level might reveal possibilities that general relativity and quantum mechanics separately cannot predict. The unification of quantum mechanics and gravity remains the greatest unsolved problem in physics. When that unification is achieved, it will almost certainly reveal new phenomena. Perhaps among them will be forms of tunneling that make current applications look primitive. Perhaps spacetime itself can be manipulated through quantum effects we have not discovered yet. Perhaps the universe has more cheat codes waiting to be found. Or perhaps we have already discovered the main ones and the future is incremental improvement rather than revolution. Either way, quantum tunneling transformed our understanding of reality and enabled technologies that define modern civilization. It made the universe comprehensible and life possible. It is fundamental to existence at every scale from subatomic to cosmic. And it represents something profound about the nature of reality. The universe permits impossibilities. Barriers are not absolute. Boundaries can be crossed without breaking them. Limitations that seem fundamental turn out to be negotiable. This is the deepest lesson of quantum tunneling. Reality is more flexible than intuition suggests. The universe operates on rules that defy common sense but work perfectly when examined mathematically and experimentally. The cosmos allows things that should not happen, and those impossible things make everything else possible. You exist because the universe cheats, because particles tunnel through barriers, because quantum mechanics is real. The impossible is routine. The forbidden is fundamental. And reality is stranger and more beautiful than anyone imagined before we looked close enough to see atoms doing impossible things. This is quantum tunneling. This is the universe's cheat code. This is why you exist. And we are only beginning to understand what else might be possible when we learn to exploit the impossible things that happen constantly all around us and inside us at scales too small to see but too important to ignore. The future will be quantum, because the present already is. And the past was built by particles doing things that classical physics says cannot happen but quantum mechanics proves happen constantly. Welcome to the quantum universe, where impossible is just another word for routine, where barriers are suggestions rather than limits, where reality itself operates on rules that defy everything our ancestors thought they knew. This is your universe, quantum mechanical, probabilistic, strange beyond imagination, and more fascinating than any fiction because it is real and because understanding it reveals both how we got here and where we might go next. The universe gave us a cheat code. We are learning to use it, and that might change everything.